Assalamualaikum. I'm Maisha Farzana from Team ENIAC. I'll provide a brief architectural overview of our digital electronics project, highlighting its key components and functionality. Our project is a digital implementation of the classic snake and ladder game, designed and simulated using Proteus software. The game board is represented as a 4x4 LED grid covering positions 0 to 15. Each blocks contain 4 LEDs, one for player 1, one for player 2, one for snakes, and one for ladders, ensuring a clear visual representation of the game state. To ensure smooth gameplay, we have constructed our design into several modules. Firstly, the dice module generates a random number between 1 and 3, simulating a dice roll on a 7-segment display. Board, snake, and ladder modules determine snake and ladder positions on board based on their lengths. The player modules show player positions. The logic module is responsible for determining the player's movement based on the dice roll. It also checks for interactions with snakes and ladders. The memory and player selector modules update and stores player positions and switches turn after each dice roll. Winning module detects when a player reaches position 15, activating LEDs to signal victory. The reset module allows restarting the game. And finally, all the modules are integrated for seamless operation, providing an interactive and engaging gameplay experience.
Assalamualaikum. I am Ortito from Team ENIAC and I'll be demonstrating the dice model. This snake and ladder game is started only when the dice is rolled. The dice determines the unpredictability of this game. When the dice is rolled, the output rapidly changes between the 2-bit numbers 1, 2, and 3. And when the button is released, the 7-segment display shows the output. Let's look into the inner configuration of this dice. To build the counter, two positive edge trigger D flip-flops are used. Two D flip-flops are used as they are the 2-bit numbers. To establish the logic that the dice only rolls between the numbers 1, 2, and 3, this sequential logic circuit is used in the counter. Let's connect the switch again to the counter and look at the outputs of the D flip-flops. We can see that the outputs are changing states between 0, 1, which means 1, 1, 0, which means 2, and 1, 1, which means 3. The outputs of the D flip-flops are connected to the PCD to 7-segment decoder. The PCD to 7-segment decoder is further connected to the 7-segment display outside. This helps to show the results from the outputs of the D flip-flops to the 7-segment display. These resistors are used as current limiting resistors in this part of the circuit. To generate the clock pulse for the D flip-flops and to drive the counter, a high-frequency clock generator circuit is added. This circuit consists of a 555 timer IC. This is configured as an stable multi-vibrator which generates continuous clock pulse. Here we have used two diodes D1 and D2. They are used to separate the charging and discharging cycles for the capacitor. This capacitor C1 determines the frequency of the oscillation, and this capacitor C2 stabilizes the circuit voltage. The resistors R1 and R3 are used as current limiting resistors for this part of the circuit. We can see here two variable resistors RV1 and RV2. They are used to control how fast the counter cycles between the numbers 1, 2, and 3. For example, if we increase the value for RV2 and look into the dice again, we'll be able to see that the output is showing the results at a much lower speed than before. This is all for the dice module. Thank you. This is the PCB design for the dice module. If we look at the 3D visualizer, the PCB board looks like this. This is the top view with the components, and this is the top view without the components. This is the bottom view, and these are the side views.
Assalamualaikum. This is Sami Akhtar Mir, and now I will be giving an overview of the ladder module, the snake module, and lastly, the board module. First up is the ladder module. This module takes two inputs, the ladder bottom and the ladder length, each ranging from 0 to 4 bits. The purpose of this module is to compute the ladder length and then light up two LEDs in the board module, one for the ladder bottom and one for the ladder top. The module outputs a total of 16 signals, each corresponding to a specific position, which are sent to the board module. Now, if we look into the internal structure of the module, we can see that a 4-bit adder will add the ladder bottom and the ladder length to determine the ladder top. Then the output of the adder goes through an OR gate. The OR gate is used so that the ladder top does not exceed the board. The outputs from that OR gate are connected to a decoder to decode the ladder top position. Similarly, the 4-bit ladder bottom input is directly connected to a second decoder to determine the ladder bottom position. To avoid contention error, we have used AND gates in our design. Jumping back to the parent sheet, let us observe how the ladder module works. If we give the ladder bottom input as binary 2 and the ladder length as binary 3, we can see that the LEDs at position 0010 and 0101 have lit up. If we change the inputs, our outputs will change accordingly. Up next is the snake module. Similar to the ladder module, this module also takes two 4-bit inputs, the snake head and the snake length. This module is used to display the snake head as snake tail in the board module. Internally, the snake module uses a 4-bit binary adder to add the complement of the snake length to the snake head to get the snake tail position. The output of the adder is passed through an AND gate to limit the snake tail position to the board. The outputs of the AND gate are then connected to a decoder to determine the snake tail position. Meanwhile, the snakehead input is directly connected to the second decoder to display the snakehead position on the board. Since these are active low decoders, AND gates are used to prevent contention errors. Returning to the parent sheet, let us observe how the snake module is in action. For example, if we set the snakehead input to binary 8 and the snake length to binary 7, we can see that the LEDs at position 1000 and 0001 have light up. Adjusting the inputs will change the outputs. Finally, we have the board module. This module consists of a 4x4 LED matrix that displays outputs from the snake module, the ladder module, and the player position decoders. Red LEDs are used for the position of player 1, blue LEDs are used to display the position of player 2, and green and yellow LEDs are used to display ladders and snakes respectively. The resistors that are connected to the LEDs have been used to limit the current passing through the LEDs so they do not get damaged. This will be all about the ladder module, the snake module, and the board module. Thank you. This is a PCB for the snake decoder module. If we take a look at the 3D visualizer, this is the top view, the bottom view, and the side view. This is the PCB for the ladder module. This is the PCB for the board module.
Assalamualaikum everyone, this is Nasif from Team ENIAC. Today I'll be explaining the snake ladder main logic module of a snake ladder game that acts as the brain of the game and performs all the necessary calculations. This module receives several inputs like the dice value, the current position of the player, the ladder bottom position, the snake head position, the ladder top position, the snake tail position, and finally an enable pin that will determine whether the game will continue or pause. And finally we have the output, which is the new position of the player. Now let's dive into the main logic. So here we can see a 4-bit parallel adder that adds the dice value and the current position of the player. It will give us a summation, and this summation will be then compared with the snake head and the ladder bottom using these two comparators. This comparison can give us three outcomes. Number one, the summation will match with either of the snake head or it will match with the ladder bottom. Option 2, the summation will match with the snake head and the ladder bottom at the same time. And number 3, the summation will not match with any one of them. Based on the output of these three outcomes, the new position of the player will be decided. Now let us go to the first one. If the summation obtained here matches with the snake head or the ladder bottom or any one of them, then the new position will be set accordingly. That is, if the summation matches with the ladder bottom, then the new position of the player will be at the ladder top. If the summation matches with the snake head, then the new position of the player will be at the snake tail. This decision here will be taken by these two 4x1 quadruple marks and this logic circuit obtained given here. This logic circuit will decide whether the new position will be at the ladder top or at the snake tail based on the output of this selection pin here. Now, going to the second option, if the summation here matches with the snake head and the ladder bottom at the same time, then this logic circuit that is connected to the selection pin of these first marks here will always give priority to the ladder. That is, if this situation occurs that the player encounters the snake head and the ladder bottom at the same time, the new position of the player will be at the ladder top instead of the snake tail. And going to the last and the third option, if the summation obtained matches neither with the snake head nor the ladder bottom, then these marks using this selection pin that is connected to the output of the comparators will just simply take the summation and pass it to the output side. And finally, we can see that there is another marks of which selection pin is connected with the carrier of the adder. It will make sure that the new position of the player never exceeds the board. That is, it never goes beyond 1 1 1 1. Now let's see whether our snake ladder main logic module works accordingly or not. So let's say the ladder length is 1001, snake length is 0111, the snake head is at 1100 position, the ladder bottom is at 0100 position. According to the length of the ladder and the snake, the ladder top is at 1101 position and the snake tail is at 0101 position. Let's say the current position is at 11. Now we will roll the dice and let's say that we are getting the value of 11. So this dice value and this current position will get added and we will get a summation of 0110 that matches with neither of the snake head nor the ladder bottom. Now according to our logic, the new position of the player should be the summation that is 0110, and yes, it is the 0110. So this condition matches perfectly. Now let us roll the dice again and let us assume that we are getting the value of 01. Now we can see that the summation obtained here is 0100, which matches with the ladder bottom. So according to our logic, the new position of the player should be at the ladder top, which is 1101, and we can see that the new position is 1101, which matches perfectly with the ladder top. This means that the ladder is working perfectly. Now again, let us assume that the current position has been promoted to 111010, and we have rolled the dice again and we are getting a value of 10. So the summation obtained here is 1100, which matches perfectly with the snake head. So according to our logic, the new position of the player should be at the snake tail, which is at 0101. And yes, the new position of the player is at 0101 that matches with the snake tail. So our snake is also working perfectly. Now let's see what will happen if the snake head and the ladder bottom are at the same position. Let's say that the snake head and the ladder bottom is at 0100. Now let's say that the current position is at 0011 and we have rolled the dice and we are getting a value of 01. So the summation here obtained is 0100, which matches with the snake head and the ladder bottom both. Now according to our logic, the new position of the player should be at the ladder top because the ladder will be getting the priority, and we can see that the new position here obtained is at 1101, which is matching the ladder top, and so our priority logic is also working perfectly. Now let's do one final checking. Let's say that our new current position is at 1110 and the dice after rolling we get the value of 11. So the logic of the snake ladder main logic module was such that the new position should not exceed the board. Now if we add this current position and this dice value, the summation obtained will cross the board. So according to our logic, this current position and the new position should be same, and we can see that yes, this current position and this new position is same. This will remain same until and unless we are getting the desired value 1 in order to reach the player to 1111. So if we get like 10, the position will not change, but if we get 01, then we can see that the position has changed to 1111. So finally we can say that our snake ladder main logic module is working perfectly with all the logics explained earlier. Thank you.
Have a look at the PCB layout of the snake ladder main logic module. So this is the PCB layout of our snake ladder main logic module. Let's have a 3D view of this PCB. So as we can see, this is the top view of the PCB. This is the front view of the PCB. These are the left and right side views. This is the back view, and this is the upside down view of the PCB. Thank you.
Assalamualaikum, I'm Tasnia Nabiha from Team ENIAC, and I'll be explaining the memory module and the player selection function in our snake and ladder game. The main job of the memory module is to store the current position of each player and update it as the game progresses. Additionally, it switches player after each dice roll. This module mainly consists of two positive age-triggered parallel-in-parallel outshift registers and a JK flip-flop. Let's start by explaining how the players switch after each dice roll. We have used a negative age-triggered 7476 JK flip-flop and we have configured it as a T flip-flop. The clock input of the flip-flop is connected to the output of the dice button. When the dice button is pressed and released, the signal goes from 1 to 0, creating a negative edge trigger for the flip-flop. So if the output Q was 1, it changes to 0, and if it was 0, it changes to 1. When Q is equals to 0, the player 1 will remain active, which actually means the register 1 will get triggered if the button is pressed. And when Q prime is equals to 0, the player 2 will remain active. The output Q is also connected to the selection pin of a mouse, which helps selecting which player's position will be passed through the main logic module to receive the updated position. Now let's look at how the memory module stores and updates the player's positions. We have used two 74195 4-bit parallel in parallel outshift registers, which receives each player's updated position from the main logic module, and when it gets triggered, the shift registers load the current position. The register 1 is triggered when Q goes from 0 to 1, updating player 1's position with the new position. And register 2 gets triggered when Q prime goes from 0 to 1, updating player 2's position. Finally, the updated position is sent to the 74154 player position decoder, which displays the new position of the player on the game board by changing the corresponding LED. So to summarize it, every time a player rolls the dice, the JK flip-flop switches turns between the players, the memory module updates the current player's position, and the decoder shows the updated position on the board, and this continues until the game ends. Now let's test if the memory module actually works as expected. Currently, Q is equals to 0, so player 1 is selected. Suppose the current position we'll get from the main logic module for player 1 is 0, 1, 0, 1. According to our logic, as soon as I press and release the dice button, the new position should be updated in the shift register output. Let's see if it works that way. As you can see, it works perfectly as the output now holds the current position. Also, we can see the player selection has already shifted to the second player. And now for the second player, suppose the new position we'll get from the main logic module is 0, 1, 1, 0. Now when I press and release the button again, we can see that the position for player 2 is currently updated in the second register. And when the turn comes back to the player 1, suppose the new position will be 1110. And when I press and release this button, it's updated accordingly. So we can confirm that the module is functioning as expected. This is how the PCB board of the memory module will look like.
Assalamualaikum, my name is Mohammad Sabdan Saqib from Team ENIAC, and I will be talking about the winning and reset modules along with the special features that we have included. In the winning module, when any of the players get to the end position, which is 1111, we get an input of 1 from the AND gate of the memory module. With this one input, we get an output of 1 from the OR gate that causes these two yellow LEDs to light up, which indicate that the game has ended. The red LED indicates that player 1 has won, and the blue LED indicates that player 2 is the winner. Moving on to the output. The 1 output from the OR gate is passed through a NOT gate, which gives an output of 0. Thus, the AND gate will also give an output of 0. This 0 output goes to the enable switch of the snake ladder main logic module, which causes the game to stop. This means that the players will not move regardless of the dice values, since 0 output is connected to both the AND gates of the enable pin. Lastly, this is how the PCB board of the winning module looks like. For the reset module, we use a switch which is normally closed. This is then open to activate the master resets of both parallel in, parallel out shift registers, which takes both the player's position to 0. Moving on to the special features. We have added the condition where the ladder top never exceeds 15. This is done by using the carry out output of the adder in the ladder module. When the sum comes greater than 15, we get a 1 output from the carry out, which is then connected to the ladder top with the OR gates. Thus, we get 111 for values which exceed more than 15. We have added a similar feature, which is that the snake bottom never goes below 0. This is done by using carryout from the subtractor of the snake position decoder module. When we get a negative number, we get 0 from carryout, which is connected to the snake tail through AND gates, which give 0000 position of snake tail when the sum is negative. After that, we have the enable pin of the snake ladder main logic module. It has two uses. Firstly, when the players are at the start, which is 0, they can only move when their dice value is 0, 1, which gives an output of 1 from both dice values to the enable pin of the snake ladder main logic module, which are basically two AND gates. For values other than 1, we get 0 output to the AND gates of the enable pin, meaning whatever the dice value, 00 will be added and the players will not move. I have explained the second case previously, which is when the game ends, we also get a 0 output to the enable pin, which also stops the game in a similar manner. We have also added a BCD to 7 segment decoder and a LED display to show which player's turn it is. We implement this using the Q output of the JK flip-flop of the memory module as input. This is then passed through a NOT gate to get 0, 1 and 1, 0, indicating player 1 and player 2. shown here. Lastly, near the end of the game, we have set a condition in which a player can only end the game when the sum of the current position and the dice is 15. If the sum exceeds this value, the player doesn't move forward. This is done by the carryout of the adder in the snake ladder main logic module, where if this value exceeds 15, we get a carryout of 1 to the multiplexer, which then takes the current position of the player and not the next position, which it normally does. Thus, the player remains at the same place, which is shown here.
Now let's see how all the modules interact to make the game work. We can get a clear idea of the total integration and transfer of bits from this diagram. At the center, we have the board module, which takes in 16-bit inputs each from the snake module, the ladder module, and the player 1 and player 2 position decoders. In the beginning of the game, the players can customize the board by selecting the position and length of the snake and ladder. The snake module takes in the snake head and snake length and calculates the tail position and sends this data as a 16-bit output to the board. The head and tail is displayed on the board using two yellow LED. Similarly, the ladder takes in the ladder bottom, the ladder length, and calculates the ladder top, and lights up two green LEDs on the board to mark its position. When the dice is rolled, it cycles from 1 to 2 to 3, and when the rolling stops, the 2-bit dice value, along with the current position of the player, is sent to the main logic module. This module also takes in the ladder bottom, the ladder top, the snake head, and the snake tail as input to determine if the player will move up or down. It adds the dice value to the current position, checks if the player has landed on a snake or ladder, and if so, it adjusts the position accordingly using logic from the main logic module. Once the 4-bit updated position is determined, it is sent to the memory module. The memory module updates and stores the new position. The new position is displayed on the board using the player position decoders. Player 1's position is shown using red LED and player 2's position is shown using blue LED. After each dice roll, the player switches automatically between player 1 and player 2, which is controlled by a 1-bit signal from the dice. The game also indicates which player's turn it is by using red and blue LEDs. The winning module checks if the player has reached the final position. It takes the 4-bit current position from the memory module, checks the current active player, and compares it with 1111 to determine the winner. The moment this happens, it turns on the winning game ending indicator and freezes the game using the enable pin of the main logic module. If at any point the player wants to restart the game, they can press the reset button, which will send a 1-bit signal to the memory module, bringing both players back to the starting position 0000 and thus resetting the board. And basically this is how all the modules interact to make the game work seamlessly.
Are you ready?
Let's play.
Assalamualaikum everyone. Let's go through one complete cycle of our snake ladder game. For the complete cycle, the snake head, the snake tail, the ladder bottom, the ladder top are set beforehand. The values are given here and here. When the red player will be active, the red LED will light up showing 1 in the LED screen. When blue player will be active, the blue LED will light up showing 2 in the LED screen. The game begins with the dice roll. So let's roll the dice. We can see a very fast randomized value in the dice LED screen. The value is 2. None of the player has proceeded because the game will not start until and unless the dice value is 1. Let's roll the dice again. No luck for none of the player. Let's roll it. Good luck for player 1 because the red one or the player 1 has proceeded 1 position ahead. Let's roll it again. No luck for the blue one or the player 2. Let's roll the dice again. So we can see that the dice value is 3. The red player of the player 1 has moved from here to here, which is at the ladder bottom. So it has been promoted to the ladder top. Let's roll the dice again. For the blue one, the value is 1, so it has proceeded 1 position ahead. Let's roll it again. The red player has moved 1 position ahead. Rolling again, the blue has moved accordingly. For the red one has moved accordingly. Again, let's roll the dice. This time, the blue one has been promoted to the ladder top because it landed on the ladder bottom. Let's roll it again for the red one. It has crossed the snake head. It has crossed this position. So in order to win the game, the red player must score 1. If it scores 2 or 3, the position will not change. So let's roll it for the blue one. The blue player has proceeded accordingly. Let's roll it again for the red one. No luck for the red one because it's 3. It needs 1. Let's roll it for the blue one. So you can see that the blue one was here. It has scored 2. It reached here, which is at the head of the snake. It was devoured by the snake and it has come to the snake tail. Let's roll it again for the red one. Let's see what happens. No luck because it needs 1. Let's roll the dice again for the blue one. The blue one has proceeded accordingly. Let's roll it again for the red one. And yes, congratulations, red one. Player 1 has won the game. The player 1 winning indicator has light up. Since one of the player has reached the final position, the game ending indicator lights up. These two yellow LEDs here and the game ending indicator. Since one of the player has won, the player indicators will not be visible again. And now since the game has ended, rolling the dice will not have any effect on the game, because this is how the game works. So finally, this is how our snake ladder game works. Thank you for watching.